Welcome to Dusk Science, or if you are here for the first journey, welcome back. The lights are low, the world outside has gone quiet, and somewhere, far above the rooftops and the streetlights, the sky is doing what it has always done, turning slowly, silently, whether anyone is watching or not. In our last journey, we followed the universe from its first moments, through the birth of galaxies, through the long and patient burning of stars, all the way toward the final light of the last ones. That was a story of beginnings, distance, and time. Tonight we go somewhere darker. Tonight we follow what can happen after the light goes out, because when a very massive star reaches the end of its life, something strange can be left behind. Not ash, not dust, not a simple ruin, something far more mysterious. A place where gravity has become so strong that nothing, not even light, can find its way back out. We call it a black hole. You do not need to understand physics to listen tonight. You do not need to remember every detail by morning. This is not a lecture, and there will be no test when the sun comes up. Think of this more like a slow walk through a very old, very dark forest, one where the trees are stars and the deepest shadows are not empty, but full of secrets that took humanity centuries to even begin to understand. Black holes have a reputation. In movies, they are often shown as cosmic monsters, violent, hungry, and dramatic, pulling everything nearby into a spinning darkness. But the real universe is often quieter than that, slower, more patient. A black hole does not hunt. It does not reach out across space looking for something to destroy. It simply exists, silently bending the space around it, the way a heavy stone bends a soft blanket when it is placed gently in the middle. That is the heart of what we will explore tonight. Not fear, but understanding. Not chaos, but a strange kind of stillness. We will begin with the simplest question. What is a black hole really? And why is the name itself only part of the truth? Then we will trace the story backward to the death of a star, because every stellar black hole began as something that once shone. From there we will approach the edge, a boundary in space called the event horizon, the last visible line before everything becomes unknown. We will imagine, calmly and without fear, what it might be like to fall towards such a place, and how time itself seems to stretch and slow the closer you get. Later, we will travel to the center of our own galaxy, where a black hole far larger than our sun sits quietly in the dark, while stars orbit around it like tiny lights circling an invisible center. We will meet even larger black holes too, giants so massive that comparing them to the sun barely feels meaningful anymore. And near the end of our journey, we will slow down even further. We will talk about how black holes, despite their reputation for permanence, may not last forever. How, over spans of time so long that all of human history becomes less than a flicker, even black holes may fade. Even they, in their own way, may come to an end. It is a strange thought to fall asleep to, that even the darkest and heaviest things in the universe are not truly eternal. But there is something peaceful in it too. Nothing in this universe holds on forever. Not stars, not light, not even the shadows they leave behind. So let your body settle, let your breathing slow. You do not need to hold on to every detail. Just let the words drift over you, the way ancient starlight drifts across the sky long after its source has changed, or dimmed, or disappeared. Tonight, we are not standing beneath a sky full of stars. Tonight, we are stepping into the space between them, into the quiet dark where black holes wait, patient, silent, and still, keeping secrets that humanity has only just begun to read. Let's begin gently. Let's begin with a gentle correction because the name itself has caused a lot of confusion over the years. A black hole is not really a hole. There is no tear in the universe. No tunnel, no opening leading somewhere else. The name is simply the closest word we had when scientists first began to understand what these objects might be. What a black hole actually is at its core is simpler than the name suggests. It is a region of space where gravity has become so strong that nothing can escape. Not a spacecraft, not a wave of radiation, not even light itself. And to understand that, we only need to begin with one idea you already know: gravity. You feel gravity every night as your body settles into the bed beneath you. It is the same gentle pull that keeps your feet on the floor, that brings a leaf drifting down from a branch, and that holds the moon in its slow orbit around the Earth. Gravity is what happens around mass. The more mass an object has, the more strongly it affects the things around it. Now imagine taking more and more mass and packing it into a smaller and smaller space. As you do that, the gravity near it grows stronger. The escape becomes harder. At a certain point, if enough mass is compressed into a small enough region, something remarkable happens. The pull becomes so strong that even light, which moves faster than anything else we know of, cannot find a path back out. That is, in the simplest possible terms, what a black hole is. Not an emptiness, not a cosmic mouth. A region where gravity has become so extreme that escape is no longer possible. It helps to let go of the image of a black hole as some kind of hungry, swirling monster in space, reaching out to swallow anything that drifts too close. That picture is dramatic, but it is not quite accurate. A black hole does not pull on distant objects more strongly than any other object of the same mass would. If our sun were somehow replaced by a black hole with the exact same mass, Earth would continue orbiting in almost the same path it follows now. We would lose sunlight, warmth, and life as we know it, but we would not suddenly be pulled inward. The danger becomes extreme only when you get very, very close. So a black hole is not a vacuum cleaner, sweeping up everything in the galaxy around it. It is closer to a very heavy, very quiet presence. Sitting in space, only truly dangerous if you wander into its immediate neighborhood. To understand how that gravity becomes powerful enough to trap light, it helps to think about space itself a little differently. We often imagine space as an empty stage, a fixed backdrop that planets, stars, and galaxies move through. But space is not fixed. And in modern physics, space and time are woven together into something called space-time. Space-time can bend, it can stretch, it can respond to the presence of mass. Picture, if it helps, a large soft blanket pulled tight and flat. If you place a small marble on it, the blanket barely dips. But if you place something much heavier in the center, the blanket curves downward, forming a deeper well. Anything rolling nearby begins to follow the curve of that dip, not because something is reaching out and grabbing it, but because the shape of the surface has changed. This is only an image, of course, but it points towards something important. In Einstein's picture of gravity, massive objects shape the space-time around them, and other things, planets, dust, gas, even light, follow the curves of that space-time. A black hole is what happens when that curve becomes unimaginably steep, so steep that there is a boundary beyond which every possible path leads inward. We will spend more time with this boundary in a later chapter when we speak about the event horizon. For now, it is enough to picture it as the edge of a very deep well in space-time, a place where the way back out has disappeared. And this is also where time begins to enter the picture, though we will save the deeper part of that mystery for later, because close to a black hole, time itself does not behave the way it does here, in the calm and ordinary stretch of space where you are resting now. Near a black hole, time can slow, distances can stretch, light can bend. The familiar rules of everyday life begin to soften at the edges. For tonight, let this simple picture settle in your mind. A black hole is not a solid object with a surface the way a planet has a surface. It is a region, a place where gravity has become so strong that light cannot escape. Not a hole torn through the universe, but a very deep, very quiet well in space-time, shaped by an immense amount of mass gathered into an impossibly small space. It is strange to think that something so powerful could form from something as familiar as a star. But that is exactly where our next chapter will take us. Because many black holes begin their lives as stars, they do not appear from nothing. They are not always dark. Before a black hole becomes a place where light disappears, it may spend millions of years as a source of light itself, a star. And to understand how a star becomes a black hole, we need to gently follow it through the final chapter of its own long life, the quiet struggle between the fire pushing outward and gravity pulling inward. We will walk through that slowly in the next part of this journey. To understand how a black hole is born, we have to go back further than its darkness. We have to go back to a time when it was still made of light. Every star you have ever looked up at is, in its own quiet way, in the middle of a long and careful balancing act. It may not look like it from here, glowing steadily in the night sky, seeming calm and unchanging. But inside every star, two enormous forces are pressing against each other, and the star's entire shape, its entire existence, depends on those forces staying in balance. The first force is gravity. A star is an immense ball of gas, and all of that gas has mass. That means all of it is pulling inward toward the center, trying to collapse the star down into the smallest and densest shape it can. If gravity had its way alone, a star would collapse inward very quickly. But something pushes back. Deep in the core of a star, under tremendous pressure and heat, atoms are being fused together. Hydrogen, the simplest and lightest element, is pressed so tightly and heated so intensely that it begins to combine into helium. This process is called nuclear fusion, and it releases an enormous amount of energy. That energy moves outward in the form of light and heat, pushing back against the inward pull of gravity. So a star, for most of its life, is simply this: a quiet glowing balance, gravity pulling in, fusion pushing out, neither one fully winning for as long as there is fuel left to burn. This balance can last an extraordinarily long time. Smaller stars, modest in mass, can burn gently for billions or even trillions of years, using their fuel slowly and patiently. But the larger stars are different. They burn brighter, they burn hotter, and they burn through their fuel much more quickly. They live brilliant lives, but in the grand span of the universe, their time is comparatively short. Eventually, for any star, the fuel begins to run low. At first, this happens gradually. The hydrogen in the core is slowly used up, and the star begins to shift toward fusing heavier elements one after another. Each new fuel burns hotter. Each new stage lasts a little less time than the one before it. It is a little like a fire that has burned through its easiest fuel and now begins reaching for whatever remains, each stage becoming shorter and more difficult. For very massive stars, this process eventually reaches a quiet but critical turning point. The core begins to form iron, and here the balance changes. Fusing iron does not release energy in the same helpful way that earlier stages did. Instead, it requires energy. So for the first time in the star's long life, the outward push begins to fail. The fire, in a sense, can no longer hold the star up, and gravity, which has been waiting patiently the entire time, finally begins to win. What happens next unfolds very quickly compared to the slow, steady burning that came before it. The core, no longer supported, collapses inward. In a matter of moments, material that once filled an enormous region of space is crushed down into something far smaller and far denser. The outer layers of the star begin falling inward too. Then, as the collapsing material meets the dense core, an immense release of energy sends the outer layers outward into space. This is what we call a supernova. It is easy to describe a supernova as violent, explosive, or chaotic, and physically it is one of the most energetic events in the universe. But tonight, we can look at it another way. A supernova is also a kind of release. The elements forged inside the star over millions of years, carbon, oxygen, iron, and more, are scattered outward into the surrounding darkness. These elements drift into space. They become part of future clouds, future stars, future planets, and perhaps eventually living things somewhere in the universe, looking up at the sky and wondering where they came from. You are made, in part, from material shaped by stars. The calcium in your bones, the iron carried in your blood, the oxygen you breathe, all of it has passed through the long story of the cosmos before becoming part of this quiet moment, here, tonight. But we are following what remains behind. After the outer layers of the star are cast outward, the core is still there, and its story is not finished. If the star was massive but not massive enough to become a black hole, the leftover core may settle into something called a neutron star. A neutron star is incredibly dense, so dense that a tiny amount of its material would weigh more than a mountain here on Earth. It is strange and remarkable in its own right, but it still has a kind of surface. It still holds itself together, but if the original star was truly massive and if the core that remains is heavy enough, gravity does not stop. There is no known force strong enough to hold the collapse back. The core continues inward, smaller, denser, quieter. It passes beyond the point where it can remain a neutron star. It folds deeper into itself until what remains is no longer an ordinary object with a surface. Instead, a boundary forms, a region of space where gravity has become so complete that nothing, not even the light that once poured from this star for millions of years, can find its way back out again. This is the birth of a black hole. Around it, there may be a brilliant supernova, bright enough to be seen across enormous distances. But at the very center of that light, something quiet has happened. A star that once shone has left behind a place where light can no longer return. And that strange boundary, that quiet edge where escape becomes impossible, is exactly where we will travel next. We call it the event horizon, and it is there that our journey continues. There is a boundary in the universe unlike any other. You cannot see it directly, you cannot touch it, knock against it, or trace your fingers along its edge. And yet it is there, quietly marking the difference between a place we can still observe and a place from which no information has ever returned to tell us what lies within. We call it the event horizon. The name itself is worth sitting with for a moment because it tells you almost everything you need to know. A horizon in the ordinary sense is the farthest place you can see. Stand on a beach at dusk and look out over the water, and the horizon is the line where the sea seems to meet the sky. It is not a wall. There is no edge of the world sitting out there. It is simply the limit of what your eyes can reach from where you are standing. The event horizon of a black hole works in a strangely similar way. It is not a surface. It is not a shell. It is not a boundary you could bump into, the way you might touch the wall of a room in the dark. It is instead the limit of what can ever return to us. Beyond it, events can still happen. Light can still be created, matter can still move, but none of that light, none of that motion, and none of that information can climb back out and reach the wider universe again. So the event horizon is not a place where a solid thing exists. It is a boundary where our ability to know what happens inside simply comes to an end. This is why it is sometimes called the point of no return. Not because something reaches out and grabs you as you cross it, the way you might imagine a trap closing shut. It is quieter than that, and in a strange way, more absolute. Once you are inside that boundary, every possible path through the future leads farther inward. Outward is no longer an option, in the same way that for you right now, tomorrow is not optional. It simply lies ahead, whether you think about it or not. It can help to let go of the idea of a wall entirely. Nothing marks this boundary the way a fence marks the edge of a field. If you were falling toward a large enough black hole, one with an especially wide event horizon, you might cross that boundary without feeling any sudden jolt at all. No barrier, no resistance, just space quietly continuing on. Except that from that point onward, gravity has curved every possible way out until escape is no longer part of what is possible. This is part of what makes black holes so difficult and so fascinating to study. We are used to understanding places by visiting them or by sending instruments to examine them, and then waiting for that information to return. A submarine can descend into the deepest part of the ocean and send its readings back to the surface. A spacecraft can travel to the edge of our solar system and still send its photographs home. Faint and delayed, but home all the same. But nothing that crosses an event horizon can send anything back. No signal, no light, no message of any kind. It is one of the only boundaries in the universe we know of that is, by its very nature, completely one-directional. So when scientists talk about a black hole size, they are not describing an object with a solid edge, the way you might describe the width of a stone or a planet. They are describing the size of this horizon, the distance from the center where gravity has become so strong that escape is no longer possible. Closer to the center, the pull only grows more extreme, but the horizon itself is the outer edge of that hidden region, the last place where light, if it were moving outward, could still have a chance to escape. Just outside it, escape is still possible. Just inside it, every future path leads inward. It is natural to wonder what lies beyond it, what the center of a black hole is really like, whether space and time continue in some form we do not yet understand, or whether our current understanding simply breaks down there. This is one of the places where science, quite honestly, reaches the edge of what it currently knows. Our equations can describe many things about black holes with remarkable accuracy. They can predict how they bend light, how they affect nearby stars, and how they shape the motion of gas and dust around them. But what happens deep inside, in the region physicists call the singularity, remains one of the great unresolved questions of modern physics. Our best understanding of gravity works beautifully on the scale of stars and galaxies. Our best understanding of tiny particles works beautifully on the smallest scales of matter, but inside a black hole, those two worlds meet in a way we do not yet fully understand. Rather than treating this as something unsettling, it may help to see it as one of the last genuine mysteries of the universe. A place where human knowledge has not yet reached, not because we have failed, but because we have not yet found the right way to ask the question. There is something quietly comforting in that if you let it settle. Even now, in an age when we can photograph galaxies from billions of years ago, there remain places the light of understanding has not yet touched. The universe has not run out of wonder. It has only run out, for now, of answers. For the rest of tonight, we are not going to try to solve that mystery. We are simply going to sit beside it, the way you might sit beside a dark and quiet lake at night, aware that its depths go somewhere your eyes cannot follow, and content for now simply to notice the stillness of the surface. But before we rest in that stillness completely, there is one more thing worth imagining gently together. What it might feel like to approach that boundary, not to cross it necessarily, just to draw near, to feel space and time begin to shift softly, the way the air changes just before a storm arrives or just before sleep finally takes you. That is where we will go next, softly, and without any hurry at all. Let us imagine gently that you are drifting through space, far from any planet, far from any sun. There is no ship humming around you, no engine, no destination waiting on a schedule, just you and the quiet dark and somewhere ahead, unseen for now, a black hole. At first, from a great distance, you might not notice anything unusual at all. Space, out here, looks much the way it always does. Stars scattered in every direction, some clustered, some alone, all of them seeming still against the darkness, the way stars often do when seen from very far away. But as you drift closer, something begins to happen to the light around you. And this is one of the more beautiful surprises about black holes. A black hole does not simply appear as a plain, flat circle of darkness sitting against the stars. Its gravity is strong enough to bend the light passing near it, so the stars behind the black hole do not simply vanish from view. Instead, their light curves around the darkness, stretching and bending into faint rings and arcs that seem to wrap gently around the black hole's edge. Astronomers call this gravitational lensing. It means that even in the presence of something that gives off no light of its own, the black hole may be surrounded by a strange and delicate glow, shaped from the borrowed light of stars far behind it. If there is matter nearby, perhaps gas or dust drawn in from a neighboring star, it may begin to spiral around the black hole before it falls in. This forms what is called an accretion disk. As this material moves closer, it heats up and begins to glow. It can form a slow, shining ring around the darkness at the center. Not every black hole has such a disk. Many black holes drift alone, quiet and almost invisible, known only through the way they bend light, disturb nearby stars, or guide the motion of gas around them. Now imagine continuing to drift closer, past the distant stars, past the bent light, past the glowing disk, if one is present, moving nearer to the region where gravity begins to take firmer hold. Here is something that might surprise you. If the black hole is especially large, one of the massive kind we will speak about later in our journey, the approach might feel strangely calm at first. Near a very large black hole, the difference in gravity between one side of you and the other can be much smaller at the event horizon than it would be near a smaller black hole, so you might drift closer and closer, crossing distances that would seem enormous to us without feeling any sudden pull. Just a slow, steady fall, silent and smooth. The stars around you beginning to shift and bend in unfamiliar ways, but nothing sudden. Nothing loud, nothing like the dramatic scenes we often imagine. Only as you move much deeper inward do the differences become more extreme. And this is where we meet one of the stranger ideas connected to black holes, something scientists sometimes call, almost playfully, spaghettification. The idea is simple. Gravity pulls more strongly on whatever is closer to its source. If a long object were falling toward a black hole, the end closer to the center would feel a stronger pull than the end farther away. Here on Earth, this difference is so small that we never notice it. Gravity feels almost even from head to toe, from one side of a room to the other, but near a black hole, especially a smaller one, that difference can become much larger. The falling object would begin to stretch along the direction of the pull, while also being squeezed from the sides. The name sounds unusual, but the idea is simply gravity becoming uneven across a small distance. There is no need to imagine it with fear. It is only physics taken to an extreme. The same gravity that gently holds you to the earth, behaving in a place where space and time have been curved far more deeply than anywhere in ordinary life. What is perhaps most fascinating about this entire journey is that it would not look the same to everyone. To you, the one falling, time would feel normal. Your thoughts would move at their usual pace. The moments would pass one after another. You would simply continue falling, watching the stars shift and curve above you, drifting steadily toward the boundary we spoke of earlier, the event horizon. And if the black hole were large enough, you might pass through that boundary without any sudden sign that you had crossed it. No wall, no surface, no sharp line, just the continuation of your path inward. But to someone watching from far away, safely distant, your journey would appear entirely different. As you approach the event horizon, you would seem to slow down more and more. Your movements would stretch out. The light coming from you would grow dimmer and redder, and from their perspective, you would appear to hover near the boundary, fading slowly from view, never quite seeming to finish the crossing at all. Two different experiences of the same fall. One person drifting smoothly onward, another far away, watching that same motion appear to slow towards something almost like stillness. This strange difference is not a flaw in the story. It is one of the clearest signs that near a black hole something fundamental begins to change. Not only space, but time And it is time, that quiet, shifting, ever-present companion of our lives, that we will turn to next. Let that thought drift gently for a moment, because in the next part of our journey, we are going to slow down together and look closely at what happens to time itself, the closer you come to the edge of a black hole. For most of your life, time has probably felt like something fixed, something steady. A clock ticks the same way in your kitchen as it does in a city on the other side of the world. A minute here feels the same as a minute there. It is easy to assume that time simply flows evenly and equally everywhere, for everyone, all at once. But that is not quite how the universe works. And one of the gentlest, strangest gifts of studying black holes is the way they reveal this to us so clearly. Time, it turns out, is not entirely separate from gravity. Wherever gravity is stronger, time itself runs a little more slowly. Not because clocks are broken, not because anything mechanical is failing, but because the actual passage of moments is different in stronger gravity compared with somewhere far away where gravity is weaker. This is not just an idea confined to black holes. It happens everywhere, all the time, though so faintly under ordinary conditions that we barely notice it. A clock sitting at the top of a tall mountain, where gravity is very slightly weaker, ticks just a little faster than an identical clock down at sea level. The difference is tiny. You would need extraordinarily precise instruments to detect it, but it is real. And it has been measured, quietly confirming something remarkable about the nature of time itself. Near a black hole, though, this effect is no longer small. It is no longer a subtle whisper you need delicate instruments to hear. As gravity grows stronger and stronger, approaching the boundary we spoke of earlier, the difference in the passage of time becomes enormous. Let us return gently to the idea of someone falling toward a black hole, the way we imagined in the last chapter. To that person, nothing about their own experience of time would feel unusual. Their heartbeat would carry on at its normal rhythm. Their thoughts would move at their normal pace. If they checked a clock they carried with them, it would tick along exactly as it always had. This is one of the more beautiful and slightly strange aspects of how time works. You never feel your own time slowing down. No matter how strong the gravity around you becomes, time from the inside always feels ordinary. It only looks different from somewhere else. And that somewhere else is where the strangeness becomes visible. Imagine that you are watching from a safe distance, far from the black hole's strongest pull, perhaps aboard some quiet drifting ship. You watch another traveler fall slowly toward the black hole below. At first, everything looks normal. But as they draw nearer to the event horizon, something curious begins to happen. Their movements begin to appear slower. Their clock, if you could still make it out, seems to tick more slowly than your own. This is not simply a trick of perspective. It is not only because they are far away. It is a genuine difference in the rate at which time is passing for the two of you, in two very different places in space-time. As the traveler approaches the boundary more and more closely, this slowing becomes more extreme. From your point of view, watching from far away, they seem to approach the edge and linger there. Their motion stretches out longer and longer. They appear to drift toward a stillness that never quite completes itself. It is not that time has stopped for them. It has not. Not from where they are. But from your side of the sky, that is how it would appear. There is a companion effect to this slowing of time, one connected closely to light itself. As light climbs outward from somewhere close to a black hole, it has to work against intense gravity to escape. And as it does, it loses some of its energy. When light loses energy in this way, it shifts toward longer, redder wavelengths. Scientists call this gravitational redshift. So the light coming from the falling traveler would not only seem slower, it would also grow dimmer. It would shift gradually toward a deeper, softer red, fading quietly into the dark rather than disappearing all at once. There's something humbling in all of this. We tend to think of time as the one truly universal thing, something every person, every star, Every planet shares equally, no matter where they are. But the universe does not work that way. Time bends, just as space does. It is shaped by gravity. It moves a little differently depending on where you happen to be standing, falling, or drifting. Somewhere, right now, close to a distant black hole, time is passing more slowly than it is passing for you, resting here in the quiet dark of your own room. And somewhere else in the open reaches of space, far from any star or planet, time may be passing just a little differently again. Not better, not worse, just different. It is not something to feel unsettled by. If anything, it is a gentle reminder of how vast and varied the universe truly is. How many different versions of now are unfolding all at once, each one shaped by its place in the cosmos. With that thought settling quietly in the background, let us turn our attention closer to home. Because at the center of our own galaxy, the Milky Way, there is a black hole, patient, quiet, invisible to our eyes, and yet powerful enough to guide the motion of stars around it. That is where we will travel next. Every night, somewhere above you, whether you can see it through your window or not, the galaxy we call home is turning slowly through the dark. It has been turning for billions of years, and it will continue to turn long after tonight has passed into memory. We call it the Milky Way. From Earth, under a dark enough sky, it can look like a soft band of light stretched across the night, faint and pale, made of more stars than the human mind can really hold at once. Our sun is only one small light among hundreds of billions, drifting in a wide, unhurried orbit around the center of the galaxy. And near that center is something we cannot see directly. Not a giant star, not a bright cluster of light, but something far quieter. A black hole, astronomers call it Sagittarius A star. It sits at the heart of the Milky Way, roughly 26,000 light years from Earth. That is an almost impossible distance to picture, but it may help to think of it this way. The light and radio waves we detect from that region have been traveling across the galaxy for about 26,000 years before reaching us. They began their journey long before written history, long before cities, long before anyone knew that a quiet dark center was waiting there. At the heart of that region lies a black hole with a mass of about 4 million suns, gathered into a space that, by cosmic standards, is remarkably small. For a long time, no one could see it. And that makes sense. A black hole emits no light of its own. Unless glowing matter is falling around it, it can sit almost perfectly hidden against the dark. So how do we know it is there at all? The answer is one of the more patient and quietly beautiful stories in modern astronomy. For decades, astronomers watched the stars near the center of our galaxy, night after night, year after year. They tracked their positions with careful attention, watching how they moved through the crowded light of the galactic core. And what they found was strange. Some of these stars were not drifting randomly. They were moving in tight, fast, clearly defined orbits around something invisible, something with no light of its own, something massive enough to guide them. One particular star, known as S2, completes an entire orbit around this unseen center in just over 16 years. At certain points in its orbit, it moves incredibly fast, sweeping around the hidden center at a small but remarkable fraction of the speed of light. For a star to move like that, around something we cannot see, only one explanation made sense. Something extremely massive and extremely compact had to be sitting there. Invisible but powerful enough to shape the motion of stars around it. Imagine for a moment that you could watch this directly, not as a violent scene, not as chaos, but as a silent, graceful dance. Stars moving in long, elegant arcs around a center that gives off no light. Their paths bending and curving around something felt, but never seen. Year after year, those stars trace their orbits again, as steady as the hands of a vast and ancient clock. This patient tracking of starlight is how we came to understand that Sagittarius A star was there. not by seeing the black hole itself, but by seeing what it does. Then, in 2022, astronomers revealed an image of the region around Sagittarius A star. They used the Event Horizon Telescope, a network of radio telescopes spread across Earth, working together like a single planet-sized instrument. The image was not a picture of the black hole itself. A black hole remains dark. Instead, it showed the glowing material and bent light around it. A faint, warm ring, a blurred halo, a circle of light surrounding a dark center. It was not sharp like an ordinary photograph. It was softer than that, more like a whisper from the center of the galaxy. But it confirmed, in a new and beautiful way, what the moving stars had already been telling us for years. There is something gently moving about all of this. The center of our galaxy is not simply a place of brightness. It is also a place of darkness. A quiet, hidden center around which nearby stars move in careful paths. Our own solar system is not close to Sagittarius A star. We are far out in one of the galaxy's spiral arms, moving slowly around the broader center of the Milky Way. But still, we are part of the same great turning system. You, in this moment, are traveling with the Earth around the Sun. The Sun is traveling around the galaxy, and far away, near the center of that galaxy, Sagittarius A star waits quietly in the dark, not pulling everything toward it, not controlling the whole galaxy by itself, but marking the hidden center of a vast cosmic structure we call home. And as enormous as Sagittarius A star feels, it is not the largest black hole in the universe, not even close. Scattered throughout the cosmos at the hearts of other galaxies, there are black holes far larger than this one. Giants with masses not in the millions but in the billions of suns. Black holes so vast that even Sagittarius A star, the dark center of our own galaxy, begins to feel almost modest beside them. It is to those giants that we will travel next, far beyond the Milky Way, into the deep, quiet places where the largest black holes in the universe rest. By now you have some sense of scale. You know that Sagittarius A star, sitting quietly at the center of our galaxy, holds the mass of about 4 million suns. That number alone can feel difficult to hold in the mind. But the universe, as it so often does, goes further still. Scattered among the galaxies that fill the visible universe are black holes that make even Sagittarius A star seem almost modest by comparison. We call them supermassive black holes, and they appear to exist at the centers of many large galaxies we have studied. Some of these black holes hold the mass of hundreds of millions of suns. Others reach into the billions. There are some whose mass is so large that ordinary comparison begins to lose its meaning. It may be more restful not to try to picture an exact number. Instead, simply sit with the idea itself. Somewhere out there, across distances almost too large to imagine, there are places where millions or billions of suns worth of mass have gathered into a region of deep and quiet gravity. Most of these giants, like Sagittarius A star, are not always bright. They are not always surrounded by glowing matter. They are not always announcing themselves across the universe. Many simply rest at the centers of their galaxies, invisible, felt through the motion of nearby stars, gas and dust. But some of them are different. Some supermassive black holes are surrounded by enormous amounts of gas and dust. This material may come from the galaxy around them, slowly spiraling inward, forming the kind of accretion disk we imagined earlier in our journey. When there is enough of this material and when it moves inward quickly enough, something remarkable can happen. The disk can become extremely hot. It can begin to shine, and in some cases, the region around the black hole can glow more brightly than all the stars in its host galaxy combined. We call these brilliant galactic centers active galactic nuclei, and in their most extreme form we call them quasars. It is worth pausing gently here to make something clear. The black hole itself, even inside all of that light, remains dark. It gives off no light of its own. What we are seeing when we observe a quasar's glow is not the black hole itself, but the matter around it. Gas and dust spiral near the event horizon. They heat up, they shine, they release energy before disappearing from view. It is a little like watching a glowing whirlpool form around a place of complete darkness. The center gives off nothing. It is the circling material around it that we are able to see. Some quasars are so distant that their light has been traveling toward us for billions of years. When we look at them, we are seeing them as they were in the early universe, when galaxies were younger, closer together, and rich with gas. In that earlier age, black holes could grow quickly. Galaxies collided more often, gas moved more freely, and some black holes became surrounded by enough material to shine across almost unimaginable distances. Compared with these bright and ancient giants, Sagittarius A is remarkably calm. It is not completely inactive. From time to time, astronomers observe small flares near the center of our galaxy, likely caused by material drifting too close and heating up before it disappears from view. But these events are modest compared with the tremendous brightness of a quasar. Our galactic center, in the grand scale of things, is quiet. It sleeps more than it burns. There is something worth appreciating in that quietness. Not every black hole spends its life surrounded by light. Not every black hole is actively drawing in great rivers of gas. Many, like the one at the center of our own Milky Way, simply remain in stillness, present but unseen, powerful but quiet, felt through their effects rather than announced by their light. It can be strange to hold both images in the mind at once. A quasar, glowing brighter than a galaxy, powered by matter moving near a black hole's edge, and our own galactic center, hidden and calm, offering only the occasional soft flicker to the instruments watching from Earth. Both are black holes, both are darkness at the center, but their surroundings tell very different stories. Some black holes are quiet, some are surrounded by light, some sleep in the hearts of galaxies for billions of years. Others briefly become some of the brightest objects in the universe. And yet, vast as these giants are, permanent as they may seem, even they are not truly eternal. Even the largest, darkest, most patient objects in the universe may slowly change, not over years, not over centuries, not even over the lifetime of stars, but across stretches of time so deep that ordinary numbers begin to feel almost meaningless. And it is there, in those almost unimaginable futures, that our journey begins to turn toward its quietest chapter yet. Because black holes, despite everything we have learned about their strength and stillness tonight, may not last forever. In the next part of our journey, we will explore, softly and slowly, how even black holes may eventually fade. Everything we have explored tonight has pointed, in one way or another, toward permanence. The event horizon, a boundary nothing can escape. Gravity so complete that even light cannot outrun it. The giants at the centers of galaxies sitting quietly for billions of years, while stars move around them in long, patient paths. It would be easy, after everything we have said, to imagine black holes as the closest thing the universe has to something eternal, fixed, unchanging, forever. But even black holes, it turns out, may not last forever. This is one of the strangest and gentlest ideas in modern physics, first proposed by the physicist Stephen Hawking in the 1970s. It suggests that black holes, despite their immense gravity, are not completely without an end. Very, very slowly, over spans of time almost impossible to picture, they may lose energy. They may lose mass, and eventually they may fade. It is worth pausing here to be honest about something. This idea, often called Hawking radiation, is a theoretical prediction. It comes from careful mathematics, bringing together our understanding of gravity with the strange and subtle behavior of the quantum world. It has not yet been directly observed coming from astrophysical black holes out in the universe. And for reasons we will come to in a moment, it may be extraordinarily difficult to observe. but it remains one of the most important and widely studied ideas in black hole physics. A quiet thread woven between two of our deepest ways of understanding reality. The idea itself, at its heart, is simple enough to hold gently in the mind without needing every technical detail. Empty space, even space that looks completely empty, is not perfectly still. On the smallest scales, it has a kind of faint activity, a subtle restlessness. Near the edge of a black hole, close to the event horizon, this deep quantum behavior may allow an extremely faint form of radiation to escape outward, a tiny release of energy, almost nothing, but not quite nothing. And if energy leaves the black hole, then the black hole loses a little mass, only the smallest amount, a whisper, not a wave. An almost immeasurably quiet exhale, repeated across a span of time so vast that human history, the age of Earth, and even the current age of the universe are only brief moments beside it. This is important to sit with gently, because it is easy to imagine this process as something dramatic, a slow leak building toward a sudden ending. But that is not really the picture. For a black hole with the mass of a star, this fading would take far, far longer than the universe has existed so far. And for the largest black holes we spoke of earlier, the supermassive giants at the centers of galaxies holding the mass of millions or billions of suns, the process would take longer still, far longer. Long after every star in the sky has gone dark, long after galaxies have drifted apart, long after the familiar bright universe has become quiet and cold. There is something strangely beautiful in the shape of that idea, even though it points toward a very distant ending. It means that the deepest darkness in the universe is not separate from time. Black holes are not outside the story. They too are part of it. They too are subject to change, however slowly that change unfolds. They too, in their own almost unimaginable way, give something back to the space around them. One faint trace at a time. It also means that black holes are not the final chapter of the universe's story, even though they may outlast nearly everything else. They are another stage, a very long stage, a very quiet stage, but not an infinite one. If you could watch the entire life of a black hole unfold, compressed somehow into a single night of sleep, its birth might happen in the first brief moment. Its long existence in darkness would fill almost the entire night. It would wait. It would curve space. It would shape the motion of nearby matter. It would remain patient and silent, while stars are born and die, while galaxies change, while the universe slowly grows older around it. And only near the very end of that impossible night, in the faintest moment before waking, would it finally fade, its mass and energy returning almost imperceptibly to the emptiness around it, until what was once a black hole becomes, in the end, indistinguishable from the quiet of space itself. This is where our journey tonight begins to turn toward its final stillness. Not an ending of drama, not an ending of sudden collapse, but something slower, softer, a future so distant that it reaches beyond stars, beyond galaxies, beyond black holes themselves, into the last quiet shape of the universe. That is where we will rest together in the final part of our journey tonight. After the last star, after the last light, into the deep and gentle dark. We have come a long way tonight, from the death of a single star to the deep quiet boundary of an event horizon, from the strange bending of time to the patient giants resting at the centers of galaxies. And now, at last, we arrive somewhere far beyond all of it, somewhere far ahead in time, past everything we have spoken about tonight. Try to imagine it gently without any need to hold the details too tightly. The stars one by one have gone dark, not suddenly, not all at once, but slowly over spans of time too long to measure in any ordinary way. The galaxies, once bright with countless points of light, have grown quiet. Their glow fades the way embers fade long after a fire has finished burning. And the black holes, Those deep, patient wells in space that we spent so much of tonight exploring have, at long last, faded too, softly, almost impossibly slowly, returning their last traces of energy to the emptiness around them. What remains in that far and distant future is space itself, vast, dark, cold, and still. Almost no light left to travel through it, no stars left to warm it, only a quiet, endless stretch, unfolding gently in every direction, with almost nothing left to disturb its silence. It is easy to hear a description like that and feel a small ache somewhere behind it, but try if you can to let that feeling soften. Because this ending, this vast and distant stillness, is not really an ending in the way we usually imagine one. It is simply the final shape the universe settles into after everything it has done and everything it has been. A long, slow exhale after a story that stretched farther than the mind can easily follow. And you, resting here right now, in this quiet room, in this quiet moment, are part of that story too. Every atom in your body was shaped somewhere along that long journey, forged in the heart of a star, scattered gently across space, gathered slowly into the earth beneath you, and eventually into you. You are not separate from any of this. You are a small, warm, breathing moment within it. A brief and gentle flicker of awareness, here to notice the universe for a little while before drifting softly into rest. There's no need to hold on to anything from tonight. No need to remember the details. No need to carry any of it forward into tomorrow. Let it settle instead the way starlight settles quietly over a dark field. Unnoticed, unhurried, simply present. Somewhere above you, whether you can see it tonight or not, the sky is still turning slowly. Stars are still shining for now. Their light is still traveling outward into the dark, the way it has for longer than we can easily imagine. Galaxies are still turning. Black holes are still resting quietly in the deep centers of space. And here, in this small, quiet place, you are simply resting too. Let your breathing slow, let your thoughts grow soft and distant, let them drift the way light drifts across the space between galaxies, unhurried and in no rush to arrive anywhere at all. The universe is vast and old and mostly quiet, and tonight, so are you. Sleep well.